Hello everyone. So in this video, we are going to discuss the uh, moving point charge. Okay. So we will consider a point charge which is moving arbitrarily and try to find out the potentials and the fields due to that moving point charge. When I mean arbitrary motion, I mean the point charge can have a velocity, acceleration, or even the derivative of acceleration can be non-zero. Okay, so it is in some arbitrary trajectory. It is executing some arbitrary motion, and in that case, what is the general form of the potentials and the electric field due to that point charge? This is what we are going to do try to understand in this video. Now, this potential and the fields of the moving point charge are referred to as the Lennard-Wickard potentials, and so this is what we're going to study here. So the way in which we'll do is basically we have all the results more or less ready. So what we are going to do is we have the general results for the retarded potential for an arbitrary charge density and current density, and we've also derived the corresponding electric and magnetic fields due to this retarded potentials. These are so-called the Jeffy-Menkos solution. Now we will consider a point charge which is moving. If we consider a point charge which is moving, then the charge density, the corresponding charge density can be written in this way in the form of a delta function, using a delta function. Okay, and even the current density can be written in the form of a delta function, where essentially this W dot or this W of t is the trajectory of the point charge, and this W dot is the velocity. Okay, this is simply the velocity of the point charge. Okay, so q times velocity times the delta function. Wherever the point charge exists, the delta function clicks. So that gives us the current density, and the charge density is given by q times the same delta function. Okay, so we are going to take this current density and charge density and substitute it back in the retarded potentials and in the electric fields here, and then simplify the formula. That's all. That's the exercise that we have to do, and we are going to do that exercise now. Okay, so it is slightly involved. It's we have to do a bit of calculation to do that, and we'll go through the steps of doing that calculation first. So here we will let's consider the potentials first. So first the scalar potential. Okay, the scalar potential, let us consider. So here there's a charge density, and we take our delta function, q times the delta function, and plug it in here for the charge density. Okay, so if I plug it in here again, this r is basically this r vector, where we are the location where we are interested in finding the potential, that thing, and the x is basically the x coordinate, which is integrated over to find the for the charge density. Okay, so this and if this is time, at the time at which we are trying to find the potential, then the charge density has to be considered at a retarded time, as we know, because these are the retarded potentials. So this is t minus r by c. Okay, this r is the distance from the charge particle, from the location of the charge particle to the position r where we are trying to find the potential. The delta function ensures that. Okay, so now again, this is a three-dimensional delta function. So if we take this and plug it in here, then we see that this is x minus w. Okay, but this is x minus w, and you might think that we can just simply do the delta function integral and just plug, take this w and plug it in here, and that will be all. But that is not all, because of a very interesting reason. Because you see, in this r also there is an x. So the delta function as a function of x is a non-trivial function. Okay, so in order to do this integral, therefore, we will apply the following trick. You can think of this more like a mathematical trick. Okay, to evaluate this integral with the delta function, we will do the following trick. What we are going to do is, we're going to call this whole of retarded time as t tilde, and we are going to introduce an integral over t tilde, and we are going to ensure that this t tilde is t minus r by c. Okay, through this additional delta function. So initially we had this three-dimensional delta function, and we introduce this additional delta function over iterated time and do an integral over iterated time. Clearly, if you do this integral over t tilde, then this delta function clicks, and this is going to be substituted here, and we are going to get back this equation. Okay, so this is just a exercise that we do. So now with this becomes independent, with this step, this becomes independent of x. As soon as this becomes, this becomes independent of x. Okay, so as soon as this becomes independent of x, then we can perform the integral over x coordinate. And once we perform the integral over x coordinate, then this w t tilde goes and sits in here. Not only it goes and sits in here, it also goes and sits in into this r here. Okay, that's what happens. So therefore, we have a new, this t tilde integral is left over. But now there's a delta function over this t tilde minus t plus r minus w of t tilde. So the problem is now shifted to just the t tilde coordinate, that now this t tilde is not, this function is not simple. It's a complicated function of t tilde, which we have to solve to perform this delta function integral. So basically what we can do is we can substitute, make a variable substitution. So let's say lambda is equal to t tilde plus this thing, this object. This thing plus this thing is our new variable lambda. So if we say that this is our new variable lambda, then lambda is some f of t tilde. F of t tilde is basically this function here. Okay, so this is nothing but f of t tilde. Okay. So this is some, it depends on the trajectory. This f tilde depends, as you can see here, this f tilde depends on the trajectory of the particle. W of t tilde is the trajectory of the particle. So it depends on that. So now if we take this lambda equals to f of t tilde as a substitution variable here, then we will see that d lambda is f prime t tilde d tilde, d t tilde. This is just a, if you just take a d on this, you'll get this. And then we take this t tilde, this expression, and plug it into our integral expression here. Okay, then we'll get f prime t tilde in the denominator, and there's a delta function f of lambda minus t tilde. And as with all variable substitutions, we have to substitute here. Everywhere you see t tildes are appearing here and here. Wherever t tildes appear, we have to substitute it with lambda. And what is lambda? Lambda is basically f inverse of t tilde. Whatever this function f is, you can formally take a f inverse, and you can say that we have to, wherever t tilde appears, we have to substitute this, right? So that we can, everything becomes a function of lambda, and then we can do the integral over d lambda. But you see, so what this integral does is basically the delta function clicks and sets lambda equals to t. That's all this integral does. Because here we have substituted this object is equal to lambda. So lambda equal to t is what the delta function is going to enforce. And therefore it simply follows that this integral, the solution of this integral is simply this thing, this object here, that everything substituted, f prime t tilde and r of t tilde is there. Okay, this r is basically this object. It is defined in this way. Okay, and then t tilde becomes equal to f inverse of t. Because why this is f inverse of t? Because here in this formula it was f inverse of lambda, but due to the delta function, lambda has become equal to t. So here all we have to do is to keep all these t tildes, and instead of substituting t tilde with respect to lambda through this equation, we substitute this t tilde using f inverse of t instead of lambda. Okay, that's all this delta function does. Okay, so that is the idea, and so then we get this solution. But now let us see what this f prime function that is coming in the denominator. So what this f prime function is, which has occurred in the denominator, it is also a function of t tilde. So this f prime function is basically this function here. This is the same function that was occurring here. Okay, this is the same function. This function we take and we have to differentiate with respect to t tilde. That's like f prime t tilde, right? So this differentiation, if you perform, you will see that this t tilde action will be on this w, the trajectory of the particle. So once you write this out, then you will see that, so you have to remember that this object is basically mod of this function. So essentially, this object is nothing but r minus w of t tilde dotted with r minus w of t tilde, right? So to the not only that, to the power half. Okay. So when the derivative acts, this becomes the same thing to the power minus half. So that minus half gives you this thing in the denominator, and in the numerator you have one of these terms. So there's a factor of 2 here, and the factor of 2 from the minus half, that would cancel. Okay. And then you have, factor of 2 from the half, the initial differentiation, and the factor of 2 here from, because there are two terms like this, those factor of, those two factors cancel out, and we have this r minus w t tilde dot differentiation of that. So the derivative with respect to t tilde, when it hits the r coordinate, that vanishes because it doesn't depend on t tilde. But when it hits the w, it gives you the velocity. So this is the velocity. Okay, and this minus sign, remains here because there's a minus sign here. Okay, so that is what you get. And you see, then it turns out to be quite simple. If you now call this whole vector as this capital R vector, okay, then this is nothing but capital R vector dotted with velocity divided by R. Okay, so a shorthand of writing this is 1 minus 1 over c times r hat times v vector. Why this is r hat? Please pay careful attention to the hats and the vectors. Okay, so because this is r vector by r, so I can say this is r hat and forget about this. So this is r hat dot velocity. So that is this term here, and then there's this factor of c. Okay, so 1 minus r hat v by c. This is the factor which is called, this f prime is a factor which is called the kappa factor, and it will appear so much in our discussion that we can give it a name. We can just call it kappa. Okay, so that is always there. So basically, therefore, we can say that this is kappa. This is some kappa times kappa is also a function of t tilde, and then there's a r of t tilde which was there in our original expression. Okay, and then at the end of the day, we have to substitute all these t tildes by solving this particular equation. Whatever the trajectory is, you give me any trajectory, I find this object, okay, where again, this, you have to remember this function f function is basically this function here. Okay, so I said that this function is equal to t, and solve for t tilde and plug it back in our final result wherever t tilde appears. That is the rule of the game. Okay, so right. So this is what we have to do. I would like you to notice that this whole operation with the delta function, what it did. What did it do? So whenever initially, if you remember, this factor was obtained from this integral. So initially we had to perform this integral, right? We had to perform this integral, right? So let me write this integral once more here, and I will convert this into a algorithm. Okay, so let's say we had to perform this integral here. Okay, and this integral, when we performed the delta function integral, what we were left with is basically we essentially got what we get here. So whatever appeared, so this is essentially, whatever these functions appeared, these functions, okay, that r became this r coordinate as a function of t tilde, and we got an additional kappa factor because of the integral over the delta function. Okay, that is the algorithm. Whatever appears in the argument of whatever multiplies the delta function, that we find at retarded time in this way. Okay, remember that this r vector, here this vector is r minus x, but this r vector is where x has been substituted, right? So this r vector is nothing but r minus w, right? W t tilde. Okay, so this r is also therefore a function of t tilde, right? So we take that, we make that substitution wherever that appears, and we divide by the factor kappa, and then we will get this answer wherever that appears. Let us remember this process and this delta function integral, because we have to do so many times. I will not describe the procedure every time, but we can just remember this fact that whatever multiplies the argument of the delta function, we can just take that argument and, that is a function of t tilde. We can make it a function of t tilde and divide by a factor of kappa, and then eventually substitute t tilde by solving this equation. And this equation we can also write as t equal to f of t tilde, right? That is the way to, that is the same thing as this one. Okay, and that is basically, this is the equation that we have to solve. Okay, so very good. So we'll just remember this, and we will proceed with the expression. So this is what I had in mind. Okay, so this factor I'm calling the kappa factor, kappa of t tilde. Okay, let's call this the kappa factor. Okay, so eventually if I write the kappa out, so it takes this form, but this factor is essentially the kappa factor. Okay, this is the kappa. Okay, and so the first result has been obtained. We have obtained the scalar potential due to a point charge. Okay, we have obtained the scalar potential, and right. So here also again I have used the notation that r hat is basically r vector divided by r. Okay, so if you like this, let's say some particle is moving, and this is at some time t is the t tilde, the location of the particle is here, and then this r, capital R vector, is the location of the, this vector starting from the location of the particle to the point of interest where we are trying to find the potential of the field. Okay, this vector is basically the r vector. Okay, so this r vector changes with time. So as let's say the particle is here and we are trying to find the field here. So this is my r vector at this time, t tilde 0, let's say, and let's say at t tilde 1 my particle is here, then this is my r vector at time t tilde 1. Okay, so the r vector changes as the particle moves through its trajectory, and therefore it is a function of t tilde. But essentially at a particular point, when it is at a location, it is as if if you take that location to be the origin, then what is the distance from the origin of the point of interest where we are trying to find the electric field, magnetic field, and the potentials. Okay, so I hope this particular algebraic manipulation is clear to you. Just go through the steps once more. Okay, so now the vector potential, that becomes super easy if we remember that algorithm. Okay, how does that become super easy? Because here this potential for the point charge we can write in this way, because this j is a function of b of t, this thing, this is a function of this t minus r, and this r is basically maybe I should write this r is as written in this expression. This r is r minus x, and there is a delta function, right? So what our algorithm tells us, we convert this v into v of t tilde and this r into r of t tilde, divide by the factor of kappa, and then put in the retarded condition. Okay, so that is what we have to do. So v becomes a function of t tilde. Okay, this is the kappa factor that was there. Okay, this is kappa. Okay, and this r is a function of t tilde now. Again, I'm using the same notation as before. Okay, so this becomes r tilde, and then we put in the retarded condition. That is the solution for the vector potential as well. It's as simple as that. So notice both the scalar potential and the vector potential. Well, the scalar potential only depends on the distance. So as you can imagine, that if the velocity of the particle is 0, then this becomes this term becomes 0, and then we immediately recover what will be the potential for a point charge, stationary point charge or static point charge, and that is basically the Coulomb's law. Okay, that is immediately recovered if we set v equal to 0 here. Okay, so similarly, if I set v equal to 0 here, the vector potential also vanishes. So that becomes the therefore this set describes essentially Coulomb's law. Okay, but if the velocity is not zero, then this term has a non-trivial contribution. Let's say even if the velocity is non-zero, but it is non-relativistic, in which we can ignore this term in the non-relativistic limit. Okay, so in the non-relativistic limit, this kappa factor is simply 1, right? Because there's a v by c, as you can see here, in this kappa factor, and that is simply 1 in the non-relativistic limit. So in the non-relativistic limit as well, this phi is well approximated by almost something like a Coulomb's law. But you see, the A vector for that, this is non-zero, then it doesn't vanish immediately. And this results in like a magnetic field as well as a modification of the electric field, as we know. And this therefore will remain. The R vector will remain as so in this final formula, the R vector will remain. This kappa factor is 1. Okay, this kappa factor is 1. Sorry, this kappa factor is 1. So this is like something like V by R that is going to remain in the formula for the vector potential. Okay, so in the non-relativistic limit, also, if there is a particle moving with some velocity, then immediately its electric and magnetic field changes, and in particular, the vector potential is non-zero, and therefore there will be a magnetic field due to its velocity. So let's say the acceleration is 0, there's just non-zero, it's moving with uniform velocity. Then we see that the vector potential will become non-zero, and it will be given by this formula. Okay, I hope this is clear. Now, let us now proceed. Again, this factor is kappa, which I said. Okay, and this is going to be a very important factor. So to summarize, we can simply write that phi is 1 over kappa times r retarded, and A is essentially velocity divided by kappa times r retarded. Okay, that is what the vector potential is. Okay, so that is the full scalar and vector potential for the point charge. Now you can start from these potentials and take the necessary derivatives. Okay, as you know, okay, this is the necessary derivative, and B is basically curl of A. Okay, and find the electric and magnetic field. Okay, you can do that, but here we have already done that exercise once while we were finding Jeffrey-Menko solution. So that is like a more general solution. And we can do the same exercise with the electric and magnetic field in the Jeffrey-Menko solution. We can perform the integral over delta function, and because we know how to perform it now, we have almost made it like an algorithm, and therefore we can just do that exercise. Although even that is a little bit algebraically intensive, so we will just proceed to do it. Okay, so let us now first consider the electric field. Okay, the electric field had 3 terms, as you know very well. These 3 terms, two of them depended on the charge density and the time derivative of the charge density, and the other was given by the time derivative of the current density. Okay, so let us look at these terms individually. So the first term is this term where there's a charge density, and this is the delta function term as we have to evaluate. Again, evaluating this is very easy. So there's a r vector here. Remember, okay. So this is the vector, okay, because there's the electric field, it has to have a direction, so this is the vector. Okay, so again, so we can take this, make it r vector as a function of t tilde, and in the denominator also we have r cube, okay, as a function of t tilde, and this additional kappa comes from the delta function integral, as we remember, and then take the retarded condition, find it at retarded time. Okay, so this is what we have to do. The symbols have their meaning here. We can immediately take this term and write the solution. Again, if you want to go through the steps, you have to do the same thing. First, introduce a integral over t tilde and call this thing t tilde, and a delta of, you have to write, delta of t tilde minus, this expression here. Okay, and then perform the x integral, and then ultimately perform the t tilde integral. That way you have to do. But essentially, this is the result if you go through all those steps. Okay. So that's the first term. What about the second term? The second term has a time derivative here. Okay, we can take the time derivative outside because these variables are different. and they are not the time variables. Of course, the time derivative only acts on the row, and because here and here, nothing depends on time. So before we perform delta function integrals, these things don't depend on time. Okay, remember. So before we perform the delta function integral, we can take the time derivative outside. Okay, before we perform the integral. Okay, now if we substitute the delta function, of course there is a q times delta function, and then if we take the steps, do the same steps as before. Okay, this becomes r vector, this becomes c times r squared, and then there's a kappa because of the delta function integral, and then that remains inside where you have to perform a derivative with respect to t tilde. So what does this mean? You have to evaluate this quantity at t tilde, then substitute t tilde in terms of t by solving this equation, and then take the derivative with respect to t. Okay, so you have to first do this substitution and then take the derivative. That is the important point. Okay, so that you have to do, so in order to avoid this step of taking a t derivative at the end, we want to take the t derivative inside. What we have to do is we have to change the differentiation with respect to t tilde coordinate. We can do that because derivative with respect to t can be written as derivative with respect to t tilde with this factor, which is dt tilde divided by dt. This factor, okay, is there. And if we know what t tilde is, right? It is given, we know what is the functional dependence of t and t tilde. It is given by this expression here. Okay, so we can take this expression and just perform a differentiation to obtain. So if we take this expression and perform a differentiation, then we obtain what is d t tilde dt. Okay, that is 1 over f prime, and that is again 1 over kappa, in our notation. Okay, this kappa of t tilde, comes in the denominator. Okay, so because of this time derivative, we can take this time derivative and make it into a t tilde time derivative and divide by 1 over kappa t tilde. But ultimately, everything is inside this retarded condition. So here, inside now, everything is a function of t tilde. But at the end of the day, we have to substitute t tilde in terms of t because using this retarded condition, because the fields that we are interested in is at time t. Okay, so we have to substitute and do this. So if you like, this t tilde or the retarded time is the time of the sources, and this t is the time of the fields at the time at which we are interested. Okay, so that is the idea, right? So this is the retarded time. Right. So now the third term. So this was the second term. That was also super easy once we knew the algorithm. Well, the main problem is this: we have this differentiation, and there are all sorts of terms here inside the differentiation. We have to perform this differentiation. We have to execute this differentiation, and that requires a little bit of algebra. Okay, and that algebra we are going to do today in this video. Okay, so now let us see what happens to the third term, which is the derivative of the current density. Okay, again we can do the same thing, take the derivative outside, and then we are left over with an integral over current density. The current density can be written as q times the velocity times the same delta function. Again, the same algorithm, change v to v t tilde, divide by the factor of kappa, and there's a factor of r coming from here. Okay, that remains here, and use the retarded condition. That's it. Okay, so now again, this differentiation with respect to t can be converted into a differentiation with respect to t tilde with this additional factor of 1 over kappa that comes in because of this variable change. Okay, so therefore this is our result for the third term as well. So now we can put all these three terms together and write down the electric field at time t is basically all these objects inside you have to calculate at retarded time. Okay, so all these are retarded time derivatives, and at the end of the day you have to use the retarded condition and substitute t tilde in terms of t. Okay, that is what you have to do. So this is more or less the result, except that now we have to perform these time derivatives. We have to perform these time derivatives and simplify the result. Okay, further. That can be simplified further. As you can see that these two time derivatives, they fit into one term where this becomes r hat minus v by c. Okay, this becomes r hat minus v by c. Okay, very good. So this is our expression for the electric field, and this is how it looks like. Now we have to, this is a little bit of algebraically intense exercise. So as you can see that when the derivative acts inside, it can act on the numerator, terms like this, and as well as it can act on the denominator on terms like kappa times r. Okay, so let us try to do this differentiation term by term and keep the results ready, and then we'll put this together. Okay, so this differentiation is a little bit intensive, but it is extremely straightforward. You know how to differentiate, right? So you can just take this derivative, let's say, so here we have r hat. So how to differentiate r hat? R hat is basically this vector divided by the magnitude of this vector, okay? And then you just take the derivative. So basically the derivative doesn't act on this r. This gives the velocity here, and the denominator remains as it is, and then you have a action on the denominator as well. When this term remains as r vector, and then it acts on the denominator, you have to remember that this object is basically the modulus, okay? So it's the modulus, so there's a power to the minus half if you write it out in terms of the vector dots. Okay, that minus half, when you differentiate, it become 3 by 2, and therefore this is going to become r cube eventually. And then you have the terms from differentiating the vectors inside. Again, the factor of 2 cancels conveniently. Okay, so this is what you have, the steps. So again, you can compactly write it in this form. Right. You can write it in this form. Right. So basically, you have r hat. Then this is also r hat because I have taken this. So there is a r square in the denominator. So I have taken it and divided r vector. So to make it into r hat. Okay, and this r hat remains as it is, and this is r hat dot v. Okay, the velocity of the vector, and then we have the r denominators as usual. Okay, so this is the first derivative, and then again this is the second one where you have to again perform this derivative over all these terms. So of course this kappa times r, when you differentiate, you will get a -1 by kappa square r square, because this is to the power -1. So you have a -1 by kappa square r square, and then you have to take the derivative over kappa times r. Okay, that you can take. You can follow these steps, and so when you differentiate kappa, then you have to differentiate these two terms, and as you can see, then there is this derivatives acting on v. Okay, you have to be careful about that. And that the derivative acting on v is precisely the acceleration. Okay, so the acceleration makes an appearance because of these terms where there were these derivatives, derivatives of t tilde. In those terms, the acceleration of the particle makes appearance in the electric field and also in the magnetic field, as you will see. But the acceleration doesn't make it appearance at the level of the potential. Okay, although the a particle can be accelerating in an arbitrary way, the potential is independent. Both the potential, the scalar potential and the vector potential, that is independent of the acceleration. Okay, it's only when you try to find the electric and magnetic field, because of the differentiation process, it becomes dependent on the acceleration as well. Okay, so now this is the acceleration of the particle. So everything is a derivative with respect to t tilde. So again, you can just go through these steps. I have written out the steps here. Okay, the derivatives I have written out. And you can go through the steps once clearly. And essentially, I do the differentiation and perform a rearranging of terms in a particular way that helps me. And right. So it is very useful to remember this kappa factor. It helps in the simplification process. For instance, here there is a term that appears, which is kappa plus r hat v by c. This is clearly 1 because kappa itself is 1 minus r hat v by c. So this factor is something which is important and useful to remember. So finally, we see that this differentiation also can be written down compactly in this form. All I have done is written this kappa factor out and differentiated. Okay, so this is just simple elementary differentiation and nothing else. I have just kept track of terms and I have called the derivative of the velocity acceleration. That's all I have done in these particular steps here. Okay, in these particular steps here, that's all I have done. Okay, so very good. So now if we try to evaluate this expression, so first the derivative will act on r hat, and then it acts on the numerator first. So this derivative is acting on r hat, and this velocity would again become acceleration, and then this derivative can act also on the denominator. So there are two terms. Now this one and this one, the derivative we have just calculated above, and we can substitute from that result. These are the results that we have just now calculated. Okay, and then at various places we see that this r hat dot v appears, that we can substitute in terms of the kappa by solving this. R hat dot v is basically c times this c times 1 minus kappa. R hat dot v is c times 1 minus kappa. Okay, so if we do that substitution, we'll find that there are some interesting cancellations that happen between terms, and then you can again rearrange these terms in a way. I've denoted with the arrows, how I have rearranged, and finally you can come up with this result here. Okay, finally you can come up with this result here, and here in the process you see also I have used another notation. So there's a term which is 1 minus v square by c square. So if you pull the c outside, then there's a 1 minus v square by c square. And as you all know, and you've encountered this this function before, so this gamma is essentially 1 by square root of 1 minus v square by c square. Okay, that makes an appearance here. Okay, and you must be wondering that you've seen this factor before in special relativity, if you have studied any special relativity, right? Here all this factor appears just out of the algebraic manipulation. Okay, I mean that is perhaps because, as I had mentioned before also, this theory of electrodynamics is secretly relativistically invariant, and therefore it kind of secretly knows about special relativity in some sense. Okay, and therefore you see all these factors floating up and giving you various interesting things. When we do relativity, we'll see that how these factors pop up there very naturally. Okay, but until we do that, this is just an algebraic exercise, and this is just a notation. Okay, this gamma is just a notation as far as we are concerned at the moment. Okay, very good. So then again we rearrange all these terms here. We rearrange all these terms, and we get all these terms. It's a bit of an intensive algebra. You can just go through these steps one by one, and finally we can come up with the fact that this derivative is basically this expression here. Okay, I've just rearranged some terms and this thing. So in the final expression, we'll have a difference of these two terms here, like r hat dot a and this vector, and minus a times the same vector here. So this it's not the same vector, it's r hat. So this thing I can write as r hat. I can rewrite as r hat times this object. Then this vector becomes the same as this vector. And then, as you can see, this can be written in terms of cross products like this. So if you just open the cross product out, you will see that this term exists. Okay, that is a part of the algebra. All right, so there are these three terms now. You see, there are these three terms that this differentiation gives me. There are three terms like this. Very good. So if there are these three terms, now originally we had to evaluate this electric field, where there's a first term here, and then there was a derivative term involving this thing. Of course, we had to divide by c times kappa factor outside, and finally, put in the retarded condition. Now, right now what we did is just evaluated this derivative. Okay, so if I plug in our result here, this result is the same result as we obtained here. Okay, we can take it and plug it in here. Okay, if we do that, then we see that the leading order terms cancel between this one and this one. This term that was there without derivative, that cancels with this leading order, this term coming from the derivative, and that these two terms are essentially replaced by a second term, which is this one. Okay, so that's quite funny, because you see this term was very much like, as I was trying to explain, this term was very much like the Coulomb's law. Okay, and that got cancelled from the derivative term. Okay, so this, you might think that what would happen to Coulomb's law? Okay, but you see that this is the term that will become Coulomb's law now, because you see, when you take the electric field and write it in this form, okay, then this term, if v is small or 0, let's say, then this kappa is 1, so you can forget about it. This term goes away. Okay, v by c is 0. Gamma, if you said v equal to 0, this is also equal to 1. Then I have r hat by r square. So that's precisely the Coulomb's law here. But the Coulomb's law gets modified in this way. Forget about acceleration. Okay, if the particle is moving with a velocity v, then immediately the Coulomb's law, the electric field, is not the same as the that you see for the Coulomb's law. Okay, it gets modified in this way as I have written down. Okay, again, remember, just to emphasize, remember that this r vector, r hat, is the relative distance, r minus the trajectory at time t tilde. Okay, that's my r vector. And eventually, again, you have to use the retarded condition and plug it in here. Okay, so there are clearly two kinds of fields in the electric field. There are two kinds of terms. In the first term, which is purely dependent on velocity, these are called velocity fields. Okay, and this is, if I take the velocity to 0, this gives rise to Coulomb's law. Okay, and then there is a new class of term which is proportional to the acceleration. If there is no acceleration, then this term vanishes. But if there is acceleration, this term remains, and these are the so-called acceleration fields. And you can note here the difference here. This one goes as r squared, and this one goes as r, 1 over r. So this 1 over r dependence at large distances, these are the terms that are going to give rise to our radiation fields. So the acceleration fields for the point charge are the ones that gives rise to radiation fields far away. Okay, that has the potential. We'll see this in more detail, but that has the potential of giving rise to the radiation fields far away. Just you can say this from the r dependence. Remember that here also r appears, but these are unit vectors. The way it appears, they are unit vectors. The way I have written it. So the r dependence is explicitly, the r dependence in the denominator is like exactly captured. Okay, of course you can set this as a vector and put in r square here, r cube here. Okay, but this is not important, but these are essentially unit vectors. So the r dependence is entirely captured here in the denominator, and this is like 1 over r, and this is like 1 over r squared. Okay, so this is more like the Coulomb's law, and this is more like an additional thing that comes in because of the acceleration of the charge. Okay, so this is what the electric field of a moving point charge is. Okay, and you can open any textbook and you will see beautiful pictures of how to picture this electric field. I'll encourage you to look at those pictures to grow some intuition. I have not reproduced them here because I have, my artistic skills are very suppressed. So I have not tried to reproduce those pictures here. But I will encourage you to look at any book and see what the form of the electric field is for this moving point charge. Let's say if it is moving at a constant velocity, or if it is accelerating, then what is the nature of the electric field you can try to draw. And this picture is often given in various books. Almost all the books that I have referred to, has this picture, except I think Landau Lifshitz. All other books I think has that picture. Okay, so that's the electric field for you. We have already done that. Okay, now what about the magnetic field? Okay, let's move on to the magnetic field. So now our job is simpler because much of our differentiation, we have already performed all these differentiations. So our job is very simple now. It's almost algorithmic. Okay, so now we can take this magnetic field and then plug in so this is written in terms of the current density, and therefore we can plug in this delta function for the current density here. There's one term which is dependent on the current density, and there's one term which is the derivative of the current density. Okay, again we can do the same thing. For this term, the current density is q times v times cross this thing. So this becomes v cross r divided by this kappa factor comes from the integral over the delta function, if you remember. That's the algorithm. Set everything as a function of t tilde here. Okay, and this is just just follows from here immediately. Okay, if you keep that algorithm in mind, and then here for this term you take the derivative outside first, outside the integral, and then you convert the stuff inside. As you can see, this becomes v cross r divided by c times kappa times r tilde. This kappa is because of the delta function integral, and this is r squared because this is r squared here. Okay, and then finally, when you convert the del t into a del t tilde, then you get an additional factor of kappa which comes in here. Okay, you get this additional factor of kappa. Okay, because of the change in derivatives. Okay, so this is with respect to t tilde now. Very good. And eventually, of course, you have to use the retarded condition and substitute back t tilde in terms of t, where this t is the time at which you are trying to find the magnetic field. Okay, so now we have to find the derivative for this one particular term that we have here, and this derivative again can act on the v, then we get acceleration simply. It can act on r hat, and we know what that result is. We have found it before here. Okay, that result we know. And similarly, the derivative can act on the denominator, del of 1 over kappa r. That result also we have found before. Okay, so we can take this term and use these two results to write this out explicitly. These two results we have found while calculating the electric field. Okay, just now, a while ago, we were discussing it. So we can take those results and plug it in here. And once we take those results and plug it in here, then we see that that there is this term. There's a v cross v term which is 0 because v cross v is 0. And then again, there is some simplification that happens between the terms. So we again, it's good to remember that we can take this r. We can take this r hat dot v and we can substitute it in terms of the kappas. Okay, that is something which is useful to remember. So, for instance, so when I write this term down, this term v cross r hat, that gives me a kappa times r here. Okay, and let me see. Yeah, so this term is this one. And then from here also, this is also v cross r, kappa square r square, that goes outside. From here also, I have a r hat cross v, which comes in here. So this is this term and this is this term. And now I can take r hat dot v outside. Sorry, r hat dot v I can take outside. This becomes kappa plus 1 r hat dot v. And this essentially, r hat dot v is c times 1 minus kappa that I have used. Then this becomes 1 minus kappa square. Okay, this term essentially becomes 1 minus kappa square. And once it becomes 1 minus kappa square, I can write this as c times 1 minus kappa square. And you see, and then rearrange the terms again. This c I can write here. This v square by c I can write here. The signs, you have to be careful. And this term goes here, and this kappa square factor cancels with the denominator here. Okay, and then this r dot a term, this acceleration term, that remains here. Okay, so that's all there is. Okay, and again you see for this term, this factor becomes a c by gamma square factor as before. Okay, and then we have two other terms like this proportional to the acceleration given by the acceleration. Okay, so this is the final result for the derivative of this term v cross r. Okay, so now let us take them and put them together for the magnetic field. And again, there was a leading term. If you remember, the magnetic field had a leading term which came from the first term in the Jeffy-Menko solution. It came from the J term. So it came from here. There was a leading term which was this term. And then there was this differentiation which we just performed now. We performed this differentiation now. So now putting it back, we see that, so this term remains as it is. And this differentiation we plug in back here. Once we do that, we see again these two terms cancel. Okay, so if you like, these two terms are cancelling. Okay, and if you like, this is somewhat similar to the Biot-Savart's law that you had. Okay, and this is the term that cancels out, and it is replaced by this object here. Okay, which has the factor of gamma square. Okay, so again, the magnetic field also has two kinds of term. One term is the so-called velocity fields. Okay, these are the velocity fields, and they have higher powers of r in the denominator. So they, in some sense, are non-zero, and they are more important near the charge. Okay, the velocity fields are more important near the charge, whereas the acceleration fields, they go as 1 over r, and therefore they are more important farther away from the charge compared to the velocity fields. Okay, so this is the structure that both the electric field and the magnetic field has a set of terms which are the velocity fields and a set of terms which are proportional to the acceleration. Okay, if acceleration is 0, then the acceleration fields are 0. And the acceleration fields, if you remember our discussion of radiation in the previous video, then you will see that these acceleration fields also go as 1 over r, and that basically tells us these acceleration fields have the potential of becoming radiation fields far, far away. So with that thought in mind, let us see what happens here. So, this is the final, result for the acceleration fields. So let us try to focus on the acceleration fields only for now. Okay, the velocity fields are there. They are non-zero near the charge, and they are there. But we are trying to focus on the acceleration fields only. Okay, let's try to focus on the acceleration fields only. Okay, so if we try to focus on the acceleration fields, then we have these two terms. And we immediately see, without taking any other approximation or any other thing, we immediately see that this electric field and magnetic field satisfy this particular relation immediately. Okay, this relation is very much reminiscent of the relationship between electric and magnetic field in electromagnetic radiation, right? What we saw last time. So how do you see that? If you just check this out once, so this is, let's say, this is like we have this thing, magnetic field is like R cross electric field. So if you just want to check this, this is the structure in the electric field, as you can see. This is the structure in the electric field. Okay, if we take this structure and cross it with the R hat, then we can do some simplification because there are too many cross products with the R. So we can do some simplification. We can take these two epsilons and we'll get two delta functions out of it. Therefore, we'll get these two terms. And once we take these two terms and simplify it again, use the fact that this object is kappa. Okay, use that fact here. Then we'll see that, again, use the fact that R cross R is 0. Okay, this is just an algebraic exercise. You will see that we get the same structure as is there in the, as is there in the magnetic field. We get the same structure here. Okay, so basically this relationship, the factors work out. You can check that the factors work out, and therefore the relationship, therefore, it holds. And so basically our objective that these relations hold. Also one thing to notice here that is also interesting, that you see, because of the cross with R, the electric field is perpendicular to the R hat direction, and so is the magnetic field. Okay, you see there's a cross with R here, there's a cross with R here. So because of that fact, both the electric field and magnetic field are also perpendicular to R hat. Okay, and they satisfy this relationship, which is very much reminiscent of the relationship between electric and magnetic fields in electromagnetic radiation. So that is all clear and good. But now let us go far away in the radiation zone. Okay, it is, this relationship holds even before going into the radiation zone far away. But now let us go far away from the, so let's say some charges, some moving here in some way here. We go very far away from the point where the charge is moving into this R vector. This is the point, location of interest. Okay, if we go very, very far away, okay, and then we will see that this R, this magnitude R can be approximated by small r here. Okay, because again, because this is very far away compared to this one. Let's say the charge is moving here, and we have, we choose our origin. So let's say the charge is moving somewhere here. Let us choose our origin here, and let's say we are interested in distance far away. Then this is approximately, this R is approximately this R. Okay, this distance. Okay, and then under this approximation, we can go ahead and find what the Poynting vector is, and we'll find that the Poynting vector under that approximation becomes essentially, these relationship between electric and magnetic fields hold. So essentially, the Poynting vector has the same form as we saw for electromagnetic radiation. It is 1 over mu naught c times the electric field magnitude square times r hat. So it is directed along the r hat direction, because there exists this relation between electric and magnetic fields, and both of the electric and magnetic fields are perpendicular to the r hat direction. Okay, in the region far, far away. Okay, so again, first, before we do anything else with this, let us focus on the non-relativistic limit that the velocities are small. Okay, it tends to 0, it's small, and therefore we can approximately take this kappa factor to be equal to 1. Okay, we can do that, and if we do that, then also in the electric field, if you remember the acceleration fields, there's this r minus v by c. So if v by c is small, we can ignore this factor, forget about this factor. So if we do that, then you see that this is r hat cross a and divided by r times c square, and if we take a magnitude, mod of this whole square, we'll get this mod of this vector squared and r square in the denominator, as happened for electromagnetic radiation. And now if we try to find the, so this is the expression for the Poynting vector, and this a square sine theta, this comes from the fact that if we take this acceleration as something, let's say, pointing towards the z-axis. So z-axis, let's say this is the acceleration, then you see this one will give you a sine square theta. This term is going to give you a sine square theta. Okay, so because this is the z-axis and r hat direction is some other direction, and this is the theta between them, right? So therefore this essentially becomes a square sine square theta, and it is directed, the Poynting vector is directed along r hat direction, and then what we have is basically this expression for the power emitted per unit solid angle. Okay, so this I want to emphasize here, that this looks very familiar from your discussion of radiation, this sine square theta. So the particle is moving like this, okay, and let's say it is moving, accelerating like this in this line, and then you know, in this region, if you consider a particular instant, then it is giving out radiation in the non-relativistic case, moving with constant velocity. Maximum radiation is given out in the perpendicular direction because of the sine theta factor. Okay, perpendicular direction to the acceleration. Maximum radiation is given out. Okay, and then the minimum radiation happens along the direction of motion. Okay, but also if it is some arbitrary trajectory and not a straight line, then this is like an instantaneous thing. We haven't performed the time averaging. Okay, this is like, you know, at a particular instance, this acceleration would have a time dependence, and that time dependence would be the time dependence of this object here. Okay, so so that is the idea. Okay, so you have to be slightly careful here, because this electric field was, you know, we had considered the electric field which is at time t. You know, let me just emphasize this point once. This acceleration fields, this was at time t, and this you had to, you know, everything inside was retarded, and eventually you had to solve this factor. So you have to solve this factor f of t tilde equal to t, and plug it in here. So the acceleration is the retarded acceleration, that you have to perform this calculation and plug it in here, and then from there you will get the e of t, and that would give you this power at, you know, if you substituted e of t here, then this will give you the power at time t. Okay, so this is the power that is, if you like, is detected. So this is the expression of the power which is detected. Okay, this is power detected far away. Okay, power detected far away. Okay, and this is pretty much the, you know, this is pretty much the expression for the acceleration, you know, in terms of this quantity. And so let's say for simplicity, let us just assume that in this non-relativistic case, this is moving with constant velocity, but it is also moving with constant acceleration, just for simplicity. Okay, then if it is moving with constant acceleration, then this term is pretty much exact, because there's no time dependence here. Then this is like a constant dp d omega. Okay, then this becomes just a constant dp d omega, because there's nothing to substitute inside. Okay, if it is constant acceleration. So very good. So let's assume that thing. We'll do the, you know, more general case, you know, very soon. We will do that. So let's see how it goes. So now I just wanted to emphasize that in the non-relativistic case, therefore, now if you take this and if you integrate this, then you will get back this so-called Larmor formula, because again sine cube theta, that will give you a 4/3, and the factor of 2 pi, that will cancel with some factors here, that is going to give you the Larmor formula. Okay, this is the same formula that we derived from the dipole formula, dipole radiation formula, just by assuming that, you know, there was a point particle which was, let's say, accelerating in some periodic motion. And so if A is periodic, for instance, if A is periodic, then you can take a time average that will give you a factor of half here, right? So then in that case you will get a factor of 1/12. Okay, If like a particle is oscillating like this with in some periodic motion, then again from this formula it is clear that that if you do the time averaging of power, that will give you an additional factor of half here. Okay, so that is what the idea is. Very good. But this formula is non-relativistic and it receives relativistic corrections. Okay. So before we go on to writing down more exact results at let's say non-zero velocity, okay, at finite relativistic velocities, I would like to make one very important point here, and that point is basically that there's a difference between, let's say the particle is moving somewhere here, okay, the particle is moving, okay, and then you're detecting it far away, okay, at time t, okay, you are detecting it far away, then so it's radiating, and it's this radiation is being detected at a distance far away at time t, and this time t, this radiation that is detected is emitted from here at a retarded time, at some retarded time t tilde, right? So there is if you like, the rate at which, so this t is different from this t tilde, so the rate at which this power is detected far away through the electric and magnetic radiation, electric and magnetic fields, that rate or the detection rate is different from the emission rate because of this difference in t and t tilde. Okay, so the detection rate differs from the emission rate because there is a difference in t and t tilde, and that we are going to flesh out here. This difference in the rate. We'll see how we can accommodate that. Okay, so basically, if we take the e's in terms of r, now instead of going into the faraway region in terms of capital R only, we can write down this electric and magnetic field in this form, and so we can calculate the Poynting vector directly, and we can say that this is the nature of the Poynting vector. Here I'm, in general this is true because this r hat vector I'm taking, I'm not approximating this r hat into r, small r hat. Okay, in general I can deal with the r hat, and I can write down this Poynting vector, and I can do this instantaneously. So this E and B fields, they are functions of time. So is the Poynting vector. This is also a function of time, right? So I can take a particular instant. Let's say some particle is moving. I can take a particular instance, find the Poynting vector, and then consider. So as I said, consider this r hat is basically the distance from this location. Okay, this r hat. This is a function of time as the particle moves through the trajectory. Okay, and then we can take this. Object, and we can now try to basically consider a sphere at very large sphere. Okay, we can try to consider a very large sphere, and we can try to find what is the power through this large sphere whose center is the location of the particle at that instant t. Okay, so if you like, this S is also a function of t, the t being the time at which you detect the electric and magnetic fields. Okay, so now if we take that and find this power per unit solid angle, sorry, what did I do? Yeah, so if you find the power per unit solid angle, then this power per unit solid angle is the one that you will detect at, if you were at a distance far away. Okay, that is the detection rate. This is the power detection rate, and therefore, so this is the detection rate. But we know that this detection rate you can write as the energy, let's say the total energy that is going, or the differential energy that is going through this surface per unit time, that is power, right? Energy per unit time, that is power. So this is dE dt, that is the detection rate. Okay, this is the power detection rate. Now if you can take this and integrate it over d omega and find P, that P would be the total power going through this surface, so the energy going through this surface per unit time at time t. Okay, so now you can say that this is the power which is being detected, but this power that is going out through this surface at large distance at time t, this was emitted by this particle at time t tilde, which was a time earlier, right? And therefore, the power which is being emitted at that time, t tilde, is basically dE d tilde, dE d tilde, but this E is the energy in the radiation. Okay, so if this is t tilde, okay, this is power per unit time that is being emitted. Okay, then we know there's a relation between t and t tilde, the retarded time and t, and that is essentially given by the f function. Okay, this is the retarded condition f function. Okay, so the power emitted is dE dt tilde, that is related to, so dE dt tilde we can convert into dE dt dt tilde, and that dt dt tilde is the so we can take this and differentiate this. So we can take this, so this is dt dt tilde is equal to f prime of t tilde. Okay, and this f prime of t tilde we know is this kappa factor. So basically this kappa factor, if we multiply with the detection rate, now this becomes d t tilde. Now this is the nothing but the detection rate. Okay, so if we multiply that with the detection rate, this factor kappa, okay, then we'll get the emission rate in terms of the detection rate. Okay, and you see there's a difference. If we are in the non-relativistic regime, that the velocities are small, then this kappa is equal to 1, and the rates are pretty much the same. But if it is moving with a very fast velocity, then these two rates are going to be different, and in general they are going to be different, and we are, they have this, difference in factors of kappa. Now, I must say that you can use, right, so I mean, you can use both the things to describe a process, right? You can say that what is the emission rate or what is the detection rate, right? You can use both the things. Okay, it just differs by the factor of kappa. Now, the point here is that if you take, in some sense, you are more interested in many cases to know the emission rate rather than the detection rate. Okay. This is because this emission rate is more like a fundamental property of the charge distribution. Okay, often you are interested in questions that, what is the energy loss of the charge distribution, etc., etc. Okay, so in that case, the emission rate is more fundamental, and it is usual when we say, power emitted per unit solid angle, it is usual to consider the emission rate instead of the detection rate, and that therefore has this additional factor of kappa in it. So therefore, we can just put in this additional factor of kappa into the formula here, and then if we put in this additional factor of kappa and use this result for the electric field, the general result for the electric field, I multiply by r square because that r square from the area element cancels the that this r square comes from the area element, if you like. Okay, so r square d omega is basically the area element. Right, so that comes from there, and so there's this thing. So now you take this and plug it in here, and you will get this formula for the emitted power per unit solid angle. Okay, so here I must say there's a little difference in the way. So of course the charge particle can execute a harmonic motion, okay, a cos or a sine. In that case, there's not much difference between that and what we discussed for the dipole, let's say, in the previous discussion. You can take that frequency and basically you can take an average, time average over it, and all the formulas kind of become the same formula as before. Okay, but it is also usual for the charged particle to move around in a trajectory and not in a harmonic motion, and therefore you have to consider the instantaneous effect, like at a particular instant, what is the emitted power? Okay, that is what you are interested in. Okay, so the question becomes slightly different for a moving charge compared to, let's say, some dipole moment of a charge distribution which is oscillating in a harmonic fashion. Okay, so that little subtlety I want you to appreciate, and that is what gives rise to this additional factor of kappa here, which goes and cancels the, so you see, k goes as kappa to the 3, and that factor gets cancelled and becomes kappa to the 5 because of this additional factor of kappa. So this is the emission rate. Okay, this is the emission rate. Very good. So right. So now we are in a, so this is the most general formula. okay, for power emitted per unit this thing, and it comes down from the radiation fields in the usual way that we just saw. Okay, so now we can ask that, so this is the most arbitrary, dependence on the angles, but we can ask for simplification, again, this has velocity, etc. So it's a slightly complicated expression. For simplicity, we can ask that what happens if the acceleration is parallel to the velocity. Okay, this is a scenario which we can study, and this is a very common scenario. Let's say an electron is moving in this direction, velocity, and let's say you stop the electron. Okay, then it will accelerate or decelerate rather in this, and it will be directed along the same direction, right? Okay, or let's say the electron is accelerating through an electric field. It is moving and accelerating in the same direction. So velocity is parallel to acceleration. Okay, many scenarios are there where this is exactly the case where velocity is parallel to acceleration. Okay. So in that case, what is it that we are going to see? Okay, so let us see what happens to this formula in that case. Here I have written the kappa factor out explicitly. Velocity is parallel to acceleration, and we are choosing the direction of the z-axis to be along that direction where velocity and acceleration points. Very good. So if we now take this, so v cross a, that term is going to vanish because velocity is parallel to acceleration. Okay, and we are going to, this numerator would reduce to this because the v cross a term cancels. Okay, and now in the denominator we'll have a r hat dot v, but v is the z direction, so r hat dot v is basically cos theta, right? Because r makes an angle of theta with the z axis. So with the choice of the z-axis along v, r hat dot v would become cos theta, right? So now with this thing, also a's direction is also, so this expression you can this dot this, you can write this as a square minus r hat dot a, that thing square. Okay, and also this r hat dot a is also along z direction, so this also will become cos theta. Okay, so there will be a square, of course, because there's a magnitude of a here. So basically you can take the a square outside, and this will become 1 minus cos squared theta divided by 1 minus v by c cos theta to the power 5. This factor was 5. You see, this factor was 5 because the kappa factor from a power of 6 reduced to 5 because of the multiplication of the kappa factor. Okay. So you see, finally we can write this formula down, where again, if you see v by c, if this goes to 0, then this is sine squared theta, and we are reduced to the previous case. Okay, so this is the generalization, if you like, for the case where velocity is parallel to acceleration. This is a generalization of that formula, of the Larmor formula, if you like. Okay, so this is a generalization of the Larmor formula, and so this formula is very interesting because you see the theta dependence is not something which is very simple now anymore. Okay, that fact that we discussed, that let's say the charge is moving and it basically radiates in the orthogonal direction, that fact is no longer true, because if the charge is moving in this direction and let's say you consider right, so I mean, there will be, so the maxima of this function is not at theta equal to pi by 2. So in some sense, theta equal to 0 direction, there still be 0. Okay, but theta equal to pi by 2 direction is not the maxima of this function. Okay, in fact, if you do the polar plots, you will see that as you increase, so this beta is basically v by c. Okay, so as you increase the velocity, okay, then this initial lobe, that would get distorted towards the direction of motion like this as you increase the velocity. Okay, so this is again a polar plot of this function for various values of this v by c. Okay, so as you can see, as you increase v by c, the maximum radiation is towards a direction which is more along the velocity direction than along the perpendicular direction. Okay, so this is very curious and interesting. You can just use any software to plot this. I've just schematically shown what is going on here. Okay, this is very important also. So, but not only that, there's something else that happens, which is denoted in this schematic diagram. That thing is, you see, if you increase v by c, you can take V by C up to 1, right? So if you increase V by C, okay, then you will see that the denominator, becomes smaller and smaller, right? If you increase V by C, the denominator becomes smaller and smaller. Let's say for for cos theta near equal to cos theta 1 or theta near equal to 0, okay, this factor is almost like 1, but then this denominator increases very much. Sorry, the denominator decreases very much, and this whole expression of power increases. So with the increase in V, the power emitted is also large. This is a very important physical point. Okay, it's not only the direction changes, the direction of maximum power emission that changes, okay, but also the magnitude of power that is emitted, that also depends on the velocity. Okay, if velocity is 0, then the magnitude is something smaller compared to if the velocity is relativistic. Okay, so that is something which is very good. So as you can see from this trend, if you really approach C, then this direction will come and be very, this maximum angle will become very close to the theta equal to 0 angle. Okay, so let us try to do an estimate of that. So let's say, we are considering the maximum angle when we are looking at the ultra relativistic limit, that the particle is moving at speeds which are very close to that light. It cannot be equal to that of light, or exceed it because of relativistic considerations. But it can be very close to that of light. So this is like, very much close to that of 1. Okay, not 1, but very close to 1, let's say. In that case, as you can see from this trend, the maximum theta is going to be close to 0. Okay, so if it is close to 0, we can expand the cos as 1 minus half theta squared. Okay, we can do that. And this 1 minus V, we can multiply numerator and denominator by 1 plus V and write this as 1 minus V square by C square, which is this gamma square factor. Okay, here, and this is 1 plus V. Okay, again, this is 1 plus V, this V by C is near 1. So this factor is not much different from 2. So we can write this as 1 by 2 gamma square. Okay, again, this gamma square is a quantity which is 1 by root over 1 minus V square by C square. So when this tends to 1, the gamma square tends to be very large, and therefore this factor is very small. Okay, so with that in mind, we can take this 1 minus V times cos theta, this factor in the denominator. We can take this and write it as 1 minus V by C times 1 minus half theta squared, that we can write. And if I write that, then I can multiply this term, and this becomes 1 minus V by C here. And then I'm left over with V by C half theta squared. Okay, that piece. Okay, I'm just trying to do an approximation and try to find out the maximum angle. Okay, that's what I'm trying to do. So now this factor is 1 over 2 gamma square, and this is half theta squared. So if I put them together, this is 2 gamma square in the denominator, and this is 1 plus gamma square times theta square in the numerator. Okay, so now this factor that appears in power, that you can write in this form. This is like 2 to the power 5, and there's a gamma square, so that's gamma to the 10 in the numerator. This sine square theta is also roughly theta. Sine theta is also roughly theta square. So this comes from the sine theta. Okay, and then in the denominator you have 1 plus gamma square theta m square. This factor remains in the denominator here to the power 5. Okay, so now if you try to find the maxima, we have to differentiate and set it to 0. So this is in that ultra relativistic regime is well approximated by this function here. And now if you differentiate and set it to 0, you will see that the solution of this is theta maximum is 1 plus minus 1 over 2 gamma square. Again, because gamma is very large, therefore this is very close to the 0. So these lobes are very much close to 0. So to conclude, if a particle is moving close to the speed of light, it is going to emit radiation along the direction of motion. But if it is moving at small velocity, then it is going to emit radiation perpendicular to the to its velocity. Okay. Of course, if it is ultra relativistic, then the amount of energy that it is emitting, that is also very large. Okay, compared to the initial condition. But I hope that this this fact about the angles, that fact is very clear to you. Okay. So this simply follows. You can estimate the minimum angle. Very good. So putting everything together, now we can take the power per unit solid angle and try to integrate it over all angles. So if you integrate it over all angles, the phi integral is going to give you a factor of 2 pi. And the theta integral is this complicated integral that you have to do. And then you can just do a variable substitution cos x equal to x here. And then, this integral you can do, right? So if you do this integral, you will get that this is equal to 4 by 3 1 minus 4 by 3 1 by 1 minus b square by c square whole cube. Okay, this you can take. This factor now again is gamma to the 6. Okay, so this is 4 gamma to the 6 by 3 that you can substitute here, and therefore in the total power, you see, you get a gamma factor. Okay, you see, this is what I was trying to say, that if it is moving with ultra relativistic speeds near to speed of light, then this is going to be very, very large. Okay, so of course, whether it would accelerate or not, that would depend on the acceleration. Whether it will emit power or not, that will depend on the acceleration. Okay, if it is not accelerating, it is not going to emit any power because the acceleration appears here, right? If it is not accelerating, it will not emit any power. But the amount of power it produces, okay, also depends on its instantaneous velocity. So if its instantaneous velocity is relativistic and it is accelerating, let's say even by a little bit, okay, then it can give out enormous power. Okay, so there's a very interesting interplay between the acceleration and velocity here. The total power depends on both acceleration as well as the velocity. Okay, in this way. Okay, so I hope that this is clear. Again, here we didn't make any non-relativistic assumption. Okay, of course you can make a non-relativistic assumption here, which is basically you can take this, in the non-relativistic limit, this is going to be equal to 1. And then we will get back with the formula that we had, the Lamarr formula. And here you will see that, that's because this 1 over epsilon naught times c cube, that is nothing but multiply by mu naught on numerator and denominator, mu naught by c. Okay, so that is what it is. So you can now basically in the non-relativistic limit, the Lamarr formula is obtained. Okay, but the interesting part is the relativistic limit, where it depends on the velocity how much it will emit. Whether it will emit or not, that will depend on the acceleration. Okay, that is the point. Okay, very good. So this thing. Now you can take the full formula. I assumed that velocity is parallel to acceleration, but instead of doing that, you can assume that what is the most general total power that is emitted. Okay, so that calculation actually I have never done somehow. Okay, all the books that I've seen, most of the books that I've seen, kind of discourages doing that because it's a complicated. Apparently, it's a complicated integral to do it most generally. Okay, but all of the books, quote the results. So I have quoted this result. You can find this result in any of the books like Zangwill or Griffiths. That result is quoted. But it is always, said that the algebra for this is very complicated. I have never tried to do it myself. So if you are interested, you can give it a hand. And if you can see that basically starting from this formula here, the general formula, okay, without assuming anything. So if you start from dp d omega formula here, the general formula, okay, you take this and if you integrate it over d omega, okay, the claim is that you will get this result here in general. Okay, for any acceleration, you'll get this result for the total power. And clearly, the total power is multiplied by this gamma to the 6 here. And when v is close to c, then this is like very, very large. This total power is very, very large. Okay, so I'm just, I've just written it down because the books tend to do that. It's just a nice result also. Okay, it's a nice result. But again, I have never, this I'm like writing down without derivation, copying from one of these books. But yeah, I have never tried to do this actually, never. So yeah, I've been very much discouraged by what books are saying. Okay. Anyway, so very good. So this more or less brings us to the end of most of the things that I wanted to say about the point charge or moving point charge. But before we terminate, there are two other things that I want to discuss, particularly relevant for the point charge. Okay, and the first thing is, so let's say I said, okay, power is emitted, electromagnetic radiation is emitted, etc., etc. But let's say a point charge is moving and decelerating along a given direction. Some moving in this direction, velocity. It is decelerating, and it is giving Bremsstrahlung. By the way, this thing that we discussed, this has a name. this thing for parallel, when velocity is parallel to acceleration, okay, so usually there are processes where the electrons are stopped by a target and it kind of decelerates to zero velocity and it gives out radiation, okay, and that radiation is generally referred to as Bremsstrahlung, and I think it's a German word, and it means breaking radiation or something like that. Okay, so that has a name. So the word Bremsstrahlung means that you're trying to decelerate an electron. In that process, the velocity is proportional to the acceleration, and in that process, it will give out radiation. Okay, so this thing. I also want you to note one very interesting thing in this formula. You see that in this formula, final formula, right, this depends on a square. Okay, because this depends on a square, it doesn't matter whether the electron is accelerating or decelerating. Okay, it's going to be the same amount. Okay, so it's not like, it's always going to emit power. It's not like when it accelerates, it emits power, and when it decelerates, it absorbs power. It's not like that. Okay, whenever there is any acceleration, positive or negative, okay, it will emit power because the power emitted depends on a square. Okay, very good. So, very good. So, with that, so you see everywhere it depends on the magnitude square. Okay, even in the general formula. Okay, so it doesn't matter. So, of course, there's one other thing that you can do. You can say that the acceleration is perpendicular to velocity. That also gives some simplification. Okay, but again, that is also a little bit of complicated algebra. So I'm like, if you are interested, you can find out what it is. The result is there in Zangwill. You can look at it. But again, that algebra is also a little bit, like a lot of algebra. Okay, so I'll just leave that to you to look at if you are interested. But this parallel thing, this phenomenon is often encountered, this phenomenon of Bremsstrahlung, and so therefore, this is very important in some sense. Right. Right. Okay, so yeah. So now I will, before finishing this discussion, let me also finish by asking a question that, let's say this electron is moving and it is emitting power, right? It is emitting power, it is moving and it is being decelerated, it is emitting Bremsstrahlung. You can ask what is the frequency of this emitted electromagnetic wave, because that is what is going to be the color of the wave, right? And of course, what this thing, it depends on the trajectory. For instance, if the electron is oscillating with some given frequency, then the electromagnetic wave will also have the same frequency. Okay, so but here, let's say it is moving and emitting Bremsstrahlung, then it will have a combination of various frequencies. It will depend on the trajectory of the electron, what kind of frequencies are there. And for in order to denote that, there's something called angle resolved frequency spectrum that one writes down. Let me just quickly tell you what that is. This is also very commonly used, so I'll tell you what that is. So basically, first, in order to appreciate that, first let us consider the Fourier transform of the electric field. Okay, again, I haven't used a different notation for Fourier transform. You can just look at the argument. It is a function of t, then it is a function of time. If it is function of omega, then it is the Fourier transform of the electric field, which is a function of t. Okay, I'm just not, in order to keep the notation simple, I could have you put in a tilde here if you like. Okay, but I'm not doing that. Okay, just not to clutter because there's already a vector sign. So I'm not doing that. Now if you take the power which is emitted, okay, let's say it's not emitted. Let's say you are considering the detected power. Okay. Let's say you are considering the detected power at far off. Okay. Now, let us say that you compute this not at a particular instant, but you are interested in finding the total power that goes through the surface at all times. Okay. Let's say you are trying to find that. Of course, this object is given by, let's say d energy dt, power per, energy per unit time. This is power. So this is d square e dt d omega. Okay. This is the power per unit time energy per unit time per unit solid angle that is being emitted. And because this is given by this expression here, this is given in terms of the electric field as a function of time, the whole thing squared. So this is a function of time, right? And basically I'm talking about the time, which is the time of the electric fields far, far away. Okay. So now if we take this expression and try to find out the total energy that is going out per unit solid angle at all times. So I'll take this expression and integrate it from time minus infinity to plus infinity. Okay. So if I do that, then this is the total energy that is going out, right? So that total energy, therefore, I will take this expression and put it in here, and I will essentially I will integrate it from with respect to time from minus infinity to plus infinity. Okay. If I integrate it with respect to time, the time dependence is gone. Okay. So now this is just the total energy per unit solid angle. Then, so now you can use this so-called Parseval's theorem. This is a result in Fourier transforms, and this is a result about Fourier transforms, that this integral here, dt integral of this thing square, is given exactly by the d omega integral of its Fourier transform. Okay. This is a result. I mean, if you can look up any math method books, I mean, this is very common. I'm sure all of you have seen this before. Also, when you did Fourier transform, this is a very, very famous and well appreciated result. Okay, it's also very useful. So now this is therefore, using this fact that this time integral is given by the frequency integral. Okay, I can take this and convert it into a frequency integral. Okay, so if I do that, then I will get that dE, this total power per unit total energy per unit solid angle. It's not power anymore. I have integrated over time to find the total power. So the total power per unit solid angle, that is given by basically the integral, the frequency integral of the Fourier transform of the electric field. Okay. So now I can use the reality condition of the electric field. Again, this is again a Fourier transform result. So if the electric field is real, that means E is equal to E star. Okay. If E is equal to E star, then E of omega must be equal to E star of minus omega. Okay. This it just follows. If you take the Fourier transform, and if you take a star here, let's say if you take a star here and say that is equal to the same result. Okay. And when you take a star here, then this minus will become plus. Okay, that therefore, you can say, then you can do a variable redefinition omega to minus omega, and you will see that this is given by, what you call the Fourier, Fourier transform of, this result just follows if E is real. Okay, so I'm saying that, this result is just true, follows from the reality of E, and you can just take a star of the Fourier transform to see that this result is true. Okay, so if E of omega is equal to E star of minus omega, and this is equal to E of omega times E star omega, okay, so then you can basically say that you can, this thing, therefore you can take and convert it, this integral you can take and convert it from to an integral from 0 to infinity instead of minus infinity to plus infinity using this, and you will get an additional factor of 2. Okay, so you will just get an additional factor of 2 here, which is going to cancel this factor of 2 here in the denominator. Okay, and right, so this factor of 2 pi came from the Fourier transform, the Parseval theorem result, and this factor of 2 would be cancelled. So once you cancel this factor of 2, you'll be left over with this result, and so this is the total energy again. This is the total energy going through a solid angle d omega, and now we can take this and we can say that this total energy is given by some frequency integral of d squared dE d omega, this object. Okay, or in other words, I can treat this as a d omega integral of some quantity. This is some quantity I'm defining. Okay, so I'm basically taking this inside the integral, and whatever I have, I'm defining as di d omega. Okay, so I can identify that. Okay, and this di d omega, this is basically the so-called angle resolved frequency spectrum. So this is the power written. This is not the power. This is the, if you like, energy written, energy per unit solid angle written in terms of frequency, per unit frequency instead of per unit time. Okay, so this is therefore this is the spectrum. Instead of writing energy per unit time, you write energy per unit frequency, and so that is basically what is known as the spectrum. So this is the frequency spectrum, and this is the angle resolved frequency spectrum, because you also know what is the angular dependence. So what this object gives you is very neatly, in terms of the Fourier transform of the electric field, you can write this, this spectrum. Okay, if you like, this is the spectrum, the angle result spectrum of this, the angle result spectrum is given in terms of the Fourier transform of the electric field. Sorry, I think I have missed a fact. Square here, right? So, so this is a measure that is often used. Instead of calculating power, you calculate the amount of energy that is that goes into some solid angle d omega and into the frequency omega. Okay, so different frequencies will get different amount of energy depending on what the Fourier transform of the electric field is. Okay, so that is the idea. Very good. So, okay, so that completes that discussion here. Now, this brings me to the last topic, and this last topic is about radiation reaction. Okay, so this radiation reaction is a very interesting thing, and it's kind of a fun topic to discuss. So, you see what is going on here. We have a bunch of charges moving around and radiating, and therefore losing out energy, right? Because they are losing out energy, therefore, if you are not doing some external work, okay, let's say, they're losing out energy on their own due to their own dynamics. Okay, that can happen. Let's say there's no external agency involved in that. Okay, so if there is no external agency involved in that radiation that is happening, then the charge configuration is losing energy, and so therefore some work is being done on the charge configuration by the fields that it creates by its own. So there's some non-trivial work that needs to be done in order to change. So basically, there's some loss of energy into radiation, right? Now, once there's some loss of energy into radiation, the charge configuration themselves loses energy. Okay, let's say there's some isolated system. So this loss of energy you can think of is basically because the electric fields of the charge configuration acts on themselves and creates a force on themselves, and that force does some work. Okay, so it is the self force of the charge configuration on itself that does some work on it, and therefore that work is basically is done in a way that it reduces its energy. Okay. So this idea gives rise to the idea of radiation reaction. Okay, so when it radiates, then there's some force, as if there's some force on it due to its own fields. Okay, so that force would be given by these, so RR here I have denoted. This is the short form for radiation reaction force. This will be given by essentially the Lorentz force kind of thing, but here these electric and magnetic field are the radiation reaction electric and magnetic fields, which are responsible for they are created by the charge density themselves in some sense. Okay, and that is what is leading to a force back on themselves. So that is a reaction force in some sense. Okay, so therefore this radiation reaction is basically a very interesting idea, that the electric fields that the charge particle creates, they themselves act a force on them, and that force does some work and reduces its energy. Okay, and where does the energy go? That is lost in the radiation that goes out and escapes the charge particles. Okay, so that is the understanding of this so-called radiation reaction force. And so now we want to see what the form of this force is. Okay, in order to see what the form of this force is, we are going to make some assumptions. We are going to say that the sources are slowly varying in time. Okay, they are as if the time dependence is slow, and also because you see there is something happening here. Of course, there's a radiation that is being emitted far away. Okay, and so the force, if there has to be a force on this here, it would have to be the electric and magnetic field in the near region rather than the far region. Okay, so we want the nature of the electric and magnetic fields in the near region. Of the sources, the charge density and the current density, and there is of course in the asymptotic the distances, large distances, there's also the radiation fields, etc. But in the near region there is also electric and magnetic field that creates some force on them, and so basically we need to deal with the near region electric and magnetic field for slowly varying charge and current densities. Okay, that's what we are going to try and understand. Okay, so but if we it's not, it cannot happen just arbitrarily. So as we see that for radiation, there's an arbitrary number of electric and magnetic fields. So if we do the multiple expansion, there are arbitrary terms in the electric and magnetic fields. There are many terms, and not all those terms actually contribute to radiation. Okay, there are only some terms that contribute to radiation that has a specific fall off. Okay, and these are the radiation fields. There are other terms in the electric and magnetic fields that are not contributing to radiation at all, and therefore their corresponding energies, they are not actually affecting the charge configuration in any way. Their energies remain as it is. There's nothing that escapes the charge configuration as such. Okay, so you can ask that what about the near region? In the near region, all these kind of fields are existent, right? In the near region, so what is so basically you have to isolate from the near region fields the terms. So let's say you do a near region multipole expansion. Okay, then you have to isolate from there the terms that are responsible for the force which reduces the energy of the configuration, right? So that those kind of terms are not apply. That will be not, of course, not all the terms in the fields and the potential. All the terms will not be responsible for reducing the energy of the configuration. So you have to carefully isolate only those terms which are responsible for reducing the energy of the configuration in the near field region. Okay, in the near region. Okay, near the sources. Okay, so this can be done using this argument, which was originally due to Dirac. You can find various versions of this argument in various places, but this was an original argument due to Dirac. So this is like a trick that one uses, okay, to isolate the terms in the retarded potential which are responsible for the force which results in the decrease in energy of the charge configuration, or the charge and current configuration. Okay, so that trick is as follows. So you know that there are two solutions to the wave equation. Okay, the retarded potentials are there, as well as there are the advanced potentials, which are the counterparts of the retarded potential, which also solve the wave equation, right? Now, the retarded waves or the retarded solutions are responsible for the radiation going out, right? They are the ones that are responsible for the charge density and charge current to radiate energy and thereby lose energy. Okay, on the other hand, the advanced counterparts, the advanced potentials, they actually are incoming waves in some sense, and these essentially result in the increase in the energy of the configuration or energy of the charge configuration, and this increase exactly happens in the same way as the retarded waves lose energy. Okay, just it follows from the symmetry of the system. There's this time reversal symmetry which I mentioned before. That is what you can use, and you can say that now the terms in the retarded waves that are responsible for taking energy out in the near field region, okay, those are the terms. The corresponding terms in the advanced wave will essentially bring in the energy. Okay, so the difference in the retarded and advanced, therefore, would be one is like carrying the energy out, and the other is like carrying the energy in. So if in the expression of the retarded solution, if we can isolate the terms that are different from the advanced solution, then those are the terms that would be responsible for bringing the radiation in, or those are the terms that will be responsible for taking the radiation out in the retarded solution, right? So I hope this argument is clear. It's a little bit of subtle argument. So I hope it is clear that the retarded waves, let me again repeat it because just in case it is not clear. So the retarded potentials, they take energy out, and the advanced potential, let's say, that bring energy in. And the way in which the energy is taken out by the retarded potential is the same way in which the advanced potentials bring in the energy, right? Now, you want to find the terms in the retarded potential that are responsible for taking the energy out. So, you compare the retarded potential with the advanced potential, the near field expansion, okay? And then you isolate the terms that are different in the retarded potential compared to the advanced potential. You know, these terms that are different, those are the terms that are responsible for bringing the energy in or taking the energy out. And therefore, we can just focus on those terms and find the force, the self force, only for those terms in the retarded potential. Okay, so again, when I do the math, it will be very clear. When I say it, maybe it's not clear. Okay, let's look at the math. So what we do. So let's take both the retarded and advanced potential. As you know, they differ by a sign here, right? One you consider the retarded time, and the other you consider the advanced time. Okay, so I have denoted that with a plus minus sign. Okay, so now if you take this and expand it in the near region, this expression is going to be small. Okay, this is small, and I'm also going to assume that this is slowly varying, so that the time derivatives of j and rho, that is also small. Okay, so this is with that approximation, because this is small, I can expand out in a Taylor series expansion. So the first term will be, I set this to 0, and the second term will be, if I take the time derivative and this factor comes out, this factor cancels this denominator, and there's a 1 over factor of c, and so on. Okay, I'm just concerned with the leading term, so I'll just keep the leading term. Okay, so this is the first term that is there, and as you can see, this plus minus comes and sits in this plus minus. So as far as this term is concerned, it is identical for both the retarded and advanced waves, but as far as this term is concerned, it is different for the advanced compared to the retarded wave. Okay, so if this term is responsible for taking the energy out in the retarded wave, this is the term that is responsible for bringing the energy in the advanced wave. So this is the term that would be responsible for the self force, which is leading to the decrease in energy of the configuration. Okay, so this is for the vector potential. We can also do this for the scalar potential. We can take the scalar potential, and we know this is the plus minus advanced and retarded here. So we can expand it out again, assuming that the rho is slowly varying with respect to time, and in the near field region, this is small. So basically the leading order term will be just this without this, and the first order term, this factor will cancel a factor in the denominator here. Okay, and the second order term, there will be a factor of this r left over here. Okay, and there will be two factors of c square. There's a half. I'm doing a Taylor series expansion, and there's a 2 into 3, 6 here, and there are three factors of coming down. One factor cancels with this denominator, and we'll get a square here. Okay, so that's what it is. I've just expanded it out in the for the scalar potential. I'm sorry. By mistake, I have written this as rho. So this is the scalar potential. So for the scalar potential, we see that there are terms like this. We see there are terms like this. This is again, these two terms are again identical in the advanced and retarded waves. Okay, whereas these terms are different in the advanced and retarded waves. And basically, I'm not saying that the advanced waves are there. That I'm not saying. I'm just using it as a tool to isolate the terms in the retarded potential. Okay, so I'm just using it as a tool. I'm not saying that you should consider advanced waves, or I'm trying to analyze advanced waves. I'm just using it in this expansion business. I'm using it as a tool to find out terms in the retarded potentials which are going to be responsible for the self force. Okay, and these will be the terms which are different from the terms in the advanced potential. And as you can see, clearly the difference is in just a sign, because we are doing this expansion out in the near field region. So it's the terms that differ by a sign. Those are the ones that are going to contribute to the self force. Okay, So now we will just isolate the terms. So that's why I have written this, this subscript. It stands for the radiation reaction terms. Okay. So the radiation reaction term for the vector potential is just going to be this term here. Okay. So I've just isolated that term and written it here. Note, I have considered the minus sign because after all, I'm dealing with retarded solutions. Okay. So I am going to deal with the retarded solutions only, but I'm going to keep track of the terms in the retarded solutions which are different from the advanced solutions, and that is justified by this fact that the advanced solution bring in energy, whereas the retarded solution take away energy. So the terms that are taking away energy, would be different from the retarded and the advanced. Okay, I hope this point is clear. Okay, it's a bit subtle. So now once you understand this point, then we are in business, because this term now can be written down in this form, that this is some time derivative of the volume integral of J. And if you remember our discussion for the radiation from this dipole radiation term that we analyzed, this volume integral of J, essentially by the use of conservation of charge, we can write it as the time derivative of the charge density, x times time derivative of the charge density, and this whole thing therefore we can write as the time derivative of the dipole moment of the configuration. Okay, just go back to the algebra that we did for dipole, to analyze the dipole radiation term. Okay, that we did in the previous video. Okay, this simply follows from there. Okay, and then there is this additional time derivative outside, which was there when, this came from the fact that we did the time expansion, right? Taylor series expansion in time. Okay, so then we can now see that the leading order term in the vector potential is a double time derivative of the dipole moment, and there's no R dependence here, quite fascinatingly. Of course, if you consider higher order terms, there will be R dependence, but there is no R dependence in the leading order term for the vector potential. Okay, so this is just a fact of the algebra that we just did. Now, not only in the other terms there will be R dependence, but also in the term that we didn't consider. For instance, this term, there would also be an R dependence. But the point is, because this term is same as the term in the advanced wave, they will not contribute to the forces that will lead to the loss in energy. Right? So that is the point. So now if you take this and right, now if you take this and if you right, so this is the expression that you will get, the algebraic expression. It's given in terms of the double time derivative of the dipole moment and no R dependence. So for phi, I had highlighted two terms here which are different in sign, this term and this one. So let's put them together and try to analyze them, and that I have called radiation reaction phi. Okay, so the first term, as you can see, it is the time derivative of the total charge, and the time derivative of the total charge, as you know, it just vanishes. Okay, this term, as you can see, it's the time derivative of the total charge, and therefore this is just equal to 0 by charge conservation. It's a total charge, it's a volume integral, so it's a full charge. So that's 0. So we are left with the second term. Okay, that's why actually, I went up to the third order, because this term was 0. Okay, had this been non-zero, I would have just stopped here. Okay, so here now, this term is the third time derivative of rho times r minus x, the whole thing square, this distance square. Okay, so this is the result. Let's keep it here. This is the retarded potential, the radiation, which are responsible for radiation reaction. Now if you try to find the magnetic field, which is the curl of A, and as you can see, there is no R dependence here. Therefore, if you take the curl, it should vanish. So there is no leading order magnetic field here, okay, for this curl of A. But what about the electric field? You see, if I try to find the gradient of phi, then the gradient goes in and hits the R square here. Okay, and if I take the gradient of this is just twice the R vector, R minus X vector, this vector. Okay, so if I do that, and so there will be a term which is, so basically if I take the gradient, act it, and this will be multiplied here, and then there will be two terms, one proportional to R and the other proportional to X. So when it is proportional to R, I can take the R vector outside, and this will be a time derivative of total charge again inside. Okay, so this will again be 0 because of charge conservation. But this other term, when x, that remains inside the integral, and there's a factor of 2. I hope I have taken care. Yeah, so the factor of 2, I have taken care here. Okay, this 24 becomes 12. Okay, there's this factor of 2 here. And now this object again becomes the dipole moment. Okay, but it is the third time derivative. So it's the like the third time derivative of the dipole moment. Okay, but we also know that the electric field has a term which goes as the time derivative of the vector potential, and the vector potential is non-zero. It's a function of time. So therefore, if we take another time derivative, then we'll also get another third derivative of the dipole moment, because the vector potential itself was the second derivative of the dipole moment, right? So therefore, you see both these terms are essentially identical with different factors in the denominator, and if you add those factors, you will see that this factor of 6 just comes out. Okay, this factor mu naught by 6 pi c, when it comes about, then you know that you are mostly on the right track. Maybe you have also got the factors right. Okay, so this is a very clear indication that we are now going to because this factor appeared in the power, right? Okay, so for a dipole, okay, this Lamarck formula for the power. So I mean, of course, it was a factor of 1/12 if you perform the time averaging, but without the time averaging, this is a factor of 1/6, right? So very good. Now, if you take the so this is the final result for the electric and magnetic field. So now, if you take this electric field and find the force on the charge itself, or the charge configuration itself, then you take charge density, multiply with this form of the electric field, and you integrate. Then for individual charges, you see, again, this is not a function of x or r anything. Okay, so this essentially becomes the total charge multiplied, that is the force. Okay, so if the total charge vanishes, okay, the total force vanishes, but there are forces on individual charges of the charge configuration. Okay, and that force on the individual charges can bring down the energy of the system. Okay, so right, I mean, can at least alter the system in a particular way. Okay, so now if we yeah, sorry, the net this thing, what I mean is on a neutral charge configuration, charge distribution on a neutral charge distribution is 0. Okay, so this is the fact. This is a fact. So now, if we take this and if we try to find the work done per unit time, because of this force, if we try to find the work done per unit time on these charges, so what we are going to do, so work done is this force dot dr. So work done per unit time is force dot the velocity. Okay, and that dr is the basically the change in location of the individual particles. So basically, I'm assuming that there are k, this is the index labeling the. So let's say there are many charged particles, and k labels labels the charges, and therefore it is summed over k, and this is the rate of doing work. And if I now try to write this rate of doing work, so this E of R dot this thing, I can bring the E outside because this doesn't depend on K in any way. Okay, we can bring the E outside, and if we bring the E outside, then this will become dot of this object. Okay, this V is basically dr dt. We can bring the ddt outside, then this becomes sum over K R, and then identifying this object again as the dipole moment of the individual charges. Okay, this object is nothing but the dipole moment written as a sum. So this is basically the time derivative of the dipole moment. So essentially, because E is given by triple time derivative of the dipole moment, so this is like the triple time derivative dotted with the single time derivative. And this triple time derivative dotted with single time derivative can be written in this way. Okay, this is the total time derivative on this. So if we act with the time derivative, we'll get a triple time derivative dot single time derivative, which is this term. And then there will be another term where this derivative acts on here. So it will be a double time derivative square. Okay, that I have to subtract out if I write it in this way. Okay, so I have written it that way. So this is basically the rate of work done on the charge configuration itself because of this radiation reaction force. Okay, so now if we try to find the average rate of work done, okay, let's say there's a harmonic motion. Okay, now let us say that there's some harmonic motion and this P is basically a periodic function. Okay, let's say sine or a cos, and therefore if we consider the time period and integrate it over one time period and divide by the time period, that is doing the time averaging, then we'll see that this total derivative in time term, this will be 0 because this is periodic, right? So if P is, let's say, sine, then P dot and P double dot, all these are sines. And so if you say that, if you do this integral, then this will be this evaluated at 0 and t, and this will just vanish, okay, because of the periodicity. Now, if you have this, this another term remains, okay, this will be the basically the time averaging of basically P double dot whole square, okay. And this, as you can see, is also the sign comes out to be minus, okay. So this is basically the amount of energy that is going to decrease on an average per unit time for the configuration, and this exactly matches with the formula, the total power emitted so the total power emitted, so that's the energy that the system is losing per unit time, that is exactly equal to this for a dipole, okay. So this is exactly the, therefore what we have done, we have been, by this, this proves, this kind of clearly shows that our, the way we isolated the terms in the potentials, in the retarded potentials, the terms in the retarded potential that were responsible for the force, for the self force, that we have been able to isolate properly. Okay, that clearly shows that. Okay, otherwise this result wouldn't have matched. Okay, so now, so this is all I had to say. This is mostly like a more general charge configuration. But what happens for a point charge? Okay, what happens for a point charge? This point charge, with respect to some chosen origin, let's say the point charge is moving around. Okay, this is basically q times the location of the point charge. That is the dipole moment, right? Let's say origin times the location. This is a single charge which is moving around. So that is the dipole moment. And therefore, if I now consider the force, this is q times the electric field, retarded part of the electric field, which we have calculated, is given by the dipole moment as the triple derivative of the dipole moment, right? And the dipole moment is this for the point charge. So this is going to give me the triple derivative of the location coordinate. Okay, so this triple derivative of the location coordinate is nothing but a single time derivative of the acceleration, because two derivatives on the location coordinate is the acceleration, and the first time derivative is the and then one time derivative on the acceleration, that is going to give me this term here. Okay, so we see that the force, the self force on the electron is proportional to the time derivative of the acceleration of the electron at that instant. Okay, so that is some very, very curious result. It's a very spooky result. So if the electron is accelerating, it creates a force on itself which is proportional to the time derivative of the acceleration. If the acceleration is constant, then there is no force. But if the acceleration is changing, let's say it changes, then it is there's a force back on the electron. Okay, due to its own fields. This is due to its own fields. Okay, so now I've given you a general understanding for a general system, but again, this is if we just take that general result and apply it for the electron, then we see that there's this term which is the self force, if you like, of the electron, and this is called the Abraham-Lorentz force, or this. Now, if you take this force and write down the Newton's law, this equation is called the Abraham-Lorentz equation, and you see, then I'll write, I can write mass times acceleration is equal to the total force. So the total force has this external force part and the radiation reaction force part. This radiation reaction force part is proportional to the time derivative of acceleration, and you get this term. It is usual to write it in this way. Okay, this is the way in which this Abraham-Lorentz equation is written. It's mass times acceleration times external force plus mass times some constant tau naught times a vector dot. Okay, the time derivative of it. Okay, so this is this tau, if you compare it with our expression here, is given by this expression divided by the mass. Okay, that is the tau naught. Okay, that is the type tau naught. Very good. So this is the Abraham-Lorentz equation, but then there is a problem with this. You see, if I, so you see, Newton's law has gotten modified. It's not only the acceleration, but the time derivative of the acceleration has also entered if it is a charged point particle. Okay, so both these things we have to assume. There's a charged particle and it's a point particle. Then Newton's law would get a modification because it is charged. It will have, Newton's law would get a term which is proportional to the acceleration, the time derivative of the acceleration. Okay, now that is immediately a problem. Okay, if this is true, then this is immediately a problem because of the following reason. Let's say there is no external forces. Okay, let's say there are no external forces. Then this is the equation that we have to solve. Okay, if it is not a charged particle, we can forget about this term. And then acceleration is equal to 0 means either it is moving with constant velocity or it is at rest. Okay. But in the presence of the charged, in the presence of the charge, let's say it's a charged point particle, then this term is there. And in general, the solution to this equation is like this, where you say that from some initial value, this object, the acceleration grows. It's like a runaway solution. You are not doing anything. You are not acting it with any force. But because of the force on itself due to its electric and magnetic fields, it seems that it would, it would say that there's some. So if there was an initial acceleration, okay, and you leave it up to itself, then it seems that there are these growing, this so-called runaway solutions that this Abraham-Lorentz equation admits. Okay, these runaway solutions are definitely, something very unphysical and very, non-intuitive physically. Of course, because these seem to be some problematic solutions. You can of course insist that this a naught is 0. Okay, you can say that this a naught is 0 and it doesn't matter if this is 0, then because this is the initial acceleration, right? So but then what happens is without giving any, if the initial acceleration is non-zero, then it's like you will see that without giving any force on it, the acceleration is going to increase. That is like an admissible solution to the equation. Okay, that is itself a very, very problem. Okay, not only this, even if the presence of external forces, okay, there are some, acausal pre-accelerations that happen, more complicated solutions that also have a problem for this, equation. So there's some problem with this equation. Okay, there's some problem with this equation, and there's a, this physical, the equation is not consistent with our physical intuitions and physical expectations. Or also, what we see, we don't see like, a moving electron, accelerating to infinite acceleration suddenly. Okay, that we don't see. Okay, so like, with time it is growing in acceleration. That kind of things, this kind of thing, runaway solution is not observed. Okay, also. So there's some problem with this. And the question is, what is the problem? And how to resolve it? I mean, there has been many takes on this. I mean, there are various ways that people have tried to understand it. So basically, this is trying to make sense of the point charge, which is an electron. Okay, not an electron. Let me say it's an attempt to make sense of the point charge and trying to reconcile it in the classical sense, where Newton's equations are valid and classical electrodynamics is valid. In that sense, we can take the point charge and try to understand how to understand. We can try to see how to interpret that point charge in the classical way. That actually, if the charge is really a point charge, that may not actually be a very good thing to do, because we know now, those kind of objects would be well described in the realm of quantum, realm of quantum field theory, let's say, or quantum mechanics in more general. We have to bring in quantum considerations, and perhaps the fact that if it is literally a point charge and we are associating some finite mass to it, maybe that is a problem. Maybe that is what the issue is, and it's probably not consistent. So it's quite legitimate to say that at the end of our discussion on electrodynamics, we kind of conclude that maybe the first thing that we started off the discussion of electrodynamics with, this static, the static point charge is all right. I mean, that's That's not a problem. But this point charge that we were talking about initially when we started off the discussion, that may not be a very good, classically well-defined quantity to consider in classical electromagnetism. That may not be true. Okay, it's maybe already an indication that we have to we have to go beyond classical electrodynamics and start doing quantum considerations of this system, and that is maybe a this thing. But again, to my knowledge, this problem, to my knowledge, I don't know if maybe there's some resolution. This problem is a problem. Like this kind of problem remains like a problem. I mean, there has been several attempts to try to understand this problem. Why this is happening. But the problem is a problem, and therefore maybe the point charge is not a well-defined object classically. Okay, that with that note, I will finish this discussion, and thanks for your attention. Okay, I'll stop the recording.